Together with my colleague here, Adrian, we're going to tell you a tale about basically how we built our own threat intelligence system from scratch and kind of what tools we used and what was our experience doing that. So you're probably wondering right now why there are two of us. So in order to build a threat intelligence system, you need two parts. You need engineering and you need security research. As you can probably read, I'm the engineering guide and Adrian is, of course, the security researcher guide. So since this is a security conference, I'll let Adrian go first and tell you about our system.
Thank you. So first of all, quick overview of our agenda. First we'll talk about what the Rapsheet is, what we understand by the term, since it's something we've been using internally. Then I'll explain how we do threat identification for our database. Dragos will walk you a bit through the engineering part, and in the end he will present some stats. Quick disclaimer, we're not presenting a product or anything here, so all we want to do is present our experience building a threat intelligence system from scratch, some lessons learned and similar, okay? So first of all, what's a rap sheet? You have some dictionary definitions if you prefer those. If not, I'll tell you it's a record the police keeps on everything bad they know someone ever did, right? So you have Al Capone's rap sheet as an example over there with a lot of stuff with his criminal history. What we did was take this idea and expand upon it by tracking all malicious IPs on the internet over time. Okay, you might ask why we want to do something like this. The reason is we are using this system live. We're generating databases of intelligence of attacks which we're using in our products. You have an example rap sheet over here. So this is a view from our internal dashboard. You can see there's a screenshot of a Barclays phishing page being served by a website from Australia. Okay. So to summarize, a rap sheet is information related to an IP address or domain, which contains proof of maliciousness in different moments in time, and for which we offer 100% certainty. So this is an internal objective that we have to respect all the time. You have another example rap sheet. It's an IP address which tries to connect to one of our SSH honeypots using commonly used credentials. One thing to understand, we're not doing any sort of moral judgment when talking about maliciousness. So to exemplify, I'll tell you that we consider malware, exploit kits, bots exploiting vulnerabilities to be dirty, phishing is dirty, but spam and porn would consider to be clean. So with porn, for example, it's clearly a matter of morality, whether you like it or not. But you might say, hey, spam is being used a lot to propagate attacks. Why are you actually naming it as clean? So the reason is there might be legitimate services, advertising services out there which are being abused to send out malicious emails. And we do not want to blacklist those. Whether or not they should be filtering the stuff they send out is, again, a discussion of morality. Okay. So on to threat identification. The easiest way you might have seen if you've ever looked at presentations about building a threat intelligence system is to do virus scanning. So you grab a couple of AV products, you start collecting some threat intelligence feeds, fetch all URLs and scan them. You will soon start having detections. As an added part, we also have to do some sort of detection thresholding. So we need at least n AV products to agree before saying that something is malicious. This is again to lower the chance of false positives. This is the easiest way to do it and what we started out doing, but it has a downside. You're basically relying on someone else's judgment. Ideally, we wouldn't want to do that. So we have to do some work of our own. Part of this is done by static analysis. If you're unfamiliar with it, it's static analysis because we're not executing malware. We're simply looking at it as a long byte string and trying to search for interesting artifacts. Okay, so we have function names, sections, entropy, certificates, all sorts of stuff. Interesting strings. So if I find a children's game and find the string Mimikatz inside, I won't assume it's the name of a character in the game, right? And you try to gather as much intel in the binary. Some examples on the slide. You can see the first one that says XOR strings. So those are names of Windows cryptography functions which have been obfuscating using XOR encryption. So that's shady, at least. The other one says anti-AV, so it's searching for commonly known security products, probably to disable or bypass. We don't yet know. And the third rectangle is a part of an info stealer, which is trying to harvest credentials from the 4 major browsers, right? Mozilla, Chrome, they're all in there. Now, we know they're showing interest for these things using static analysis, but we don't have 100% proof. So to do that, we have to do dynamic analysis, actually executing the binary in a sandbox. We used Cuckoo Sandbox to set things up. It's a great project. It's open source. I highly recommend you try it if you want to do some threat intelligence research of your own in sandboxing. You will quickly learn that you have to do some sort of VM or sandbox hardening. So it's not hardening as in protecting against exploits, but hardening against malware which tries to detect it's being analyzed and stop its execution. So you have to convince it is running in a real environment and not analysis. Okay, Cuckoo does some of this work for you. You also have to do some of your own because malware creators know about Cuckoo. You might ask why use VMs if they're easy to spot. The reason is that they're also easy to revert and reuse. Alternatively, you could execute on bare bones hardware, but you would have very slow cleanup. So it's not magnitude of hours like cleaning up Windows XP used to be when you had viruses, but it's still too slow for an automated environment. So we have execution. We started analyzing behavior. To give the malware a helping hand, you also want to add some honey on your machine, okay? By installing applications, maybe vulnerable versions of applications, by leaving some fake documents lying around, fake credentials, anything they might be interesting in exfiltrating. Then you start grabbing intel, and you will find a lot of it. You will find dropped files, you will find IPs, contacted IPs, botnet CNCs, and all the actions that undertook. So, as you might imagine, dynamic analysis offers great power when doing this, and as the old saying goes, with great powers comes responsibility, right? Because you are executing malware and you would like to prevent some things from happening. So it's nice not to spam others, because overloading the internet is not very nice. If you don't care about the niceness thing, just think that gathering spam is useful for threat intelligence. It can offer a lot of insight. You also don't want to DDoS others, so some people might say, hey, I'm just going to buy 1,000 IoT devices, hook them up to the internet, run malware, and see what happens. And the next time a country gets knocked off the internet, you know who's to blame. You also don't want to brute force credentials for other websites, infect other people, and this is all sometimes easier said than done, because you need to build a large cage around your environment to block these things, but you also want to create something like a cozy home for malware to feel safe and do all its malicious bidding, right? So this is an ongoing process that requires a lot of constant monitoring and evaluation. So this was talking about the client side. We also have the server side, public-facing services to consider. And for those, we used honeypots. Probably people have heard of honeypots. We're using low interaction honeypots, which mimic legitimate services, such as Dioneea, which is an SMB, SQL, FTP, and multiple services honeypot. Kipper and Cowrie for SSH and Telnet, GlassTopF for web exploits, and others. A lot of great projects. I don't have enough time to name them all. And ideally, the best way to gain as much intelligence as possible, you want to do some globe trotting. You want to deploy in different continents, in different countries, in a lot of different providers, and you will quickly learn that this becomes hard to administer because everyone is using a different sort of VM template, different basic operating system, and you start having issues deploying your system. So to solve this, we took a page from the enemy's playbook, and we said, hey, if they can fast flux their CNC servers, we should definitely be able to proxy our honeypots. So proxy machines, as we call them, are lightweight machines which only do traffic redirection towards the real honeypots in the backend. They're easy to deploy, very fast. They don't have dependency OS issues. They're just firewall rules, right?
Also, on the easy to deploy part, just think IP tables, and that's it.
Yeah, that's the main thing they're doing. This also solves another issue of honeypot blacklisting. So if at one point you see you don't have any more traffic on one box because it's been blacklisted as a honeypot, you just take it quickly, deploy on another part of the internet, and you're done. So you're using just one jar, which is easy to administer, right, to catch a whole lot of flies, and dumping data to your central repository. In our case, we also have one more issue to consider, and that is false positives. Because internet traffic, will consist of a lot of scanners. So do we consider scanners to be malicious or not? Our rating is not, because if they're not actively exploiting a vulnerability and just checking for it, they're not necessarily malicious. You have indexing bots, real or fake. Sometimes you will find the real Google bot, sometimes you will find someone impersonating it. Again, if it's not doing any active exploitation, we consider it to be non-malicious. We only want to identify attacks, and the best way we found so far is to actually create signatures for those attacks, so more signature work. Okay, one more threat I'd like to talk about is phishing. Y'all know phishing comes in all sizes, flavors, colors, whatever you want to call them. Whenever there's some sort of major breach somewhere, it started with a phishing email. So we tried our hand at phishing detection, even though it's a very difficult problem. And one way to do it is using static signatures for the larger targets out of the internet. But this quickly becomes unfeasible because there are a lot of challenges. So you have signature development, first and foremost. You have to create a signature. Then you don't want it to have any false positives, which might be a problem because sometimes you will have, because you will always match the original page, right? So the page being cloned. Sometimes it's not an issue because we actually found people phishing pages of phishing, so they just cloned the phishing page, and I can only assume the chain goes on forever. You have to redo them periodically because the original page will change from time to time. And you also have limited detection. They're very easy to bypass. So a page only has to look Facebook-y, Google-ish enough to fool a user into inserting his or her credentials, right?
Or one way of bypassing them directly is just do a screenshot of the actual page, just post an image there. So
yeah, we actually saw that in action. One page and one photo, sorry. So our other alternative was to create a generic method. We tried our hand at creating a machine learning-based detection approach. We have a framework which accesses websites, processes the HTML code, and then tries to classify correctly as phishing or non-phishing. It works better than signature-based detection, of course, but it also has the problem of false positives. So it requires a lot of monitoring, and we generally rely on a second opinion before saying that a page is phishing or not.
Also, while training the phishing engine, we managed to block Google access for the whole of Ixia because you need some false positives in your training set. So what better way to get them than crawl the first 10 pages of Google for some search terms?
Okay, so that's about it, about the threats. We have more stuff that we're doing, but not enough time to cover them all. I'd like to talk to you about one more useful tool, and that is passive DNS. So if you're familiar with it, or unfamiliar with it, it's the passive gathering of DNS-related data. We could have used a provider, but we decided to build our own database since we're actually crawling a whole lot of the internet. So we're tracking host names, domains, and IP address, and we found this to be valuable information that people could probably use in a lot of different scenarios. So for example, you can do some sort of whitelisting since people use threat intelligence to blacklist stuff, okay? You might say, this has been a Google IP for the past 2 years. I don't want to risk blocking it because it appears to be a false positive. You will have reoccurrences, and reoccurrences a lot of times are caused by having poorly disinfected websites. So there's a malicious iframe, it gets removed, gets added again, gets removed, because people don't always fix the underlying vulnerabilities. So the website is still easy to compromise. One more thing, which we don't necessarily do, but there's a lot of interest in, I think there's another talk in the other track about this, is mapping threat actors. So you can use all of this data. You can also correlate with binary information, with public information, and then you can find information about the threat actor who is trying to compromise your network.
Of course, you can also use passive DNS to find new domains to crawl and scan as well for the system. So
yes. Okay, so that's about it from me. As you might imagine, this system has a lot of moving components. It gathers a lot of data. This raises some interesting engineering challenges, which my colleague Dragos will talk about next.
Okay, so engineering is up next. Let's see. So if you take a look at our system from a 10,000-mile view, you'll see that it basically takes in URLs, binaries, and honeypot attacks, processes them through multiple nodes in the system, and then produces at the end Rapsheets, as well as tracking information for different entities or items within our system. So we track a lot of binary hashes in the form of SHA-256 hashes, domains, IPs, and URLs. And based on the information we gather on those, for example, for SHA, we might gather the detections or the static analysis information or the dynamic analysis information. Or for a domain, we might gather all of the related IPs and other information like that. Using this information, we create what's called a rap sheet. And you saw an example earlier. The rap sheet is basically proof that we have legitimate reasons to block an IP, okay, over there. So the system itself is organized as a graph of connected nodes where each node in the system does one small and specific thing to analyze what's coming in. So you can think, for example, as an example of a node, you have the fetcher, which basically takes in an URL and using a headless browser like Phantom.js actually accesses that URL and retrieves the contents of it and stores it for later scanning. So we periodically crawl different threat intelligence feeds, both private, public, and our own feeds gathered from spam. And using those URLs, we fetch them, we store their contents, and then analyze them using AVs, dynamic analysis, static analysis, phishing scanners, as Adrian talked, as well as a whole host of other components. And all of these components are tied together in a graph. Each component does its own specific thing. It takes some input and produces some output. So some facts about our system. For one, it's a real-time system. So as soon as we have enough information to build a rap sheet, we actually build it and publish it. And this information with the rap sheets goes into our threat armor device for now. And basically, clients get protected as soon as we have information about a malicious IP. So the whole system, if you're familiar, raise your hand if you're not, is based on the data flow model. So in it, each node, as I've said, receives some input and produces some output. For example, the fetcher receives URL to fetch and produces fetch contents. The nodes themselves are connected in a topology. You can rearrange the topology however you want. You can reuse the nodes however you want. The nodes can also interact with external services like databases, storage systems, sandbox execution. For example, we have something called the sandbox analysis component, which, based on information about the binary, will choose which VM in the sandbox to submit it to. So for example, if the file is an Android APK, it will choose a VM for Android. Or if we've determined via static analysis that it's using some specific Windows functions, we will submit it to a VM running the Windows at the specific version required for those functions that it's using. Okay, one more thing to note, you can also have special nodes in the system. These are nodes that basically produce only output. One such node in our system is called the collector, which periodically scans threat intelligence feeds for URLs and binaries and pushes them through the system for scanning. Another type of special node is one that only receives input. So you can think of this as the end node that once it has all of the information, it aggregates it in the DB and populates all of our nice little entities like IPs, SHAs, URLs, or domains. So you might wonder why choose this specific model in order to build our system. Well, for once, as I've said, each node does one tiny little thing. So because of that, it's easy to develop and test and iterate through it. It's also easy to reuse. You can connect the same node in multiple places in your system. And it's also easy to reason about at the node level. It's easy to understand its interaction. And when you look at the whole system topology, you'll understand how the flow of information works through it. And one added benefit to this, we can also auto-document the system. So when you look at the topology, you have instant system documentation. Okay. As I've said, the nodes can be combined in different ways of topology. One more important thing is things are separated, like in a microservices architecture. You can scale nodes individually. So if you need more processing power, for example, for AV detection or for the sandbox, you can just scale that part. You don't need to touch the other parts of the system. Since it's a topology, new nodes can easily be added wherever you need them in the topology, and each node can be updated individually. So if you just need to change something in the fetcher, in the way you're fetching URLs, for example, add a new user agent or support in the headless browser or something, you just update that specific node. So you don't need to touch the other while the system is running. Okay, so now that I've talked about how the system is organized, let's see how we actually store our data. So we have two types of data in our system. One is blob data. You can think of it as the contents of fetched URLs, packet capture, dropped files, and sandbox analysis results generated by Cuckoo Sandbox, screenshots, as well as other types of binary data that flow through our system. For this, we use a cloud storage system. Currently, we're using Amazon S3, but we've also abstracted so that we can easily move to something else if the need arises. Now, the other more important part is the way we store structured data. So for structured data, this is our actual DB, and we're using a NoSQL multimodal DB called Arango. So why multimodal? It's pretty easy for it to ingest information. So you can store key value pairs, you can store document objects, and one more important thing we're using right now, you can have a graph database. Graph database basically means that you can have relationships between entities in your database, and we'll take a look at our data model on the next slide. But for now, the main advantage of Arango is that it's really, really flexible. So it's NoSQL based. You have a schemaless architecture for it. You can just post JSON objects and it will store them without any hesitation. And this makes it easy to add new fields and information as you're going on and developing and adding more and more to your system. And finally, you also get the world of SQL databases. So you get a query language. In this case, it's called AQL from Arango query language. You get transactions, indexes, and joins, as you would get in a normal DB. So, as I've said, we also have our specific data model for storing stuff in our DB. This is a high-level overview of it. Of course, there are many more entities and relationships in the database, but to get a picture of how the graph works, we have four main entities: domains, IPs, SHAs, and URLs, and we have different relationships between them. For example, a domain resolves to an IP, right? This is one relationship, and this basic relationship, together with a domain, is connected to another domain, for example, via an NMS, MX, or CNAME entry. These two relationships help form our passive DNS system. So you just have two relationships for every passive DNS query you need to answer. Another relationship, of course, is URL fetches to SHA. So using this relationship, for example, we can determine all the URLs that fetch to a particular SHA, as well as all of the SHAs generated by an URL. You also have URL redirects to another URL. We can use, and we're currently using this type of relationship in order to track URL redirect chains to see how an URL was fetched and through what other hops it went through. And of course, between URL and domain, we have the basic hostname relationship, which you can use to see, for example, all of the URLs that are known for a specific domain. Okay, so this is a basic overview of how our main data model looks like in our system. And it's, as you can see, it's pretty easy from a security researcher perspective to understand it. Right? Okay, so why choose this particular way of storing it in a graph? For one thing, the graph maps normally to any problem domain, which of course is the internet. So if what we're trying to achieve is a graph, why not model it as a graph? So this lets us do a lot of interesting queries, like, for example, one particular one is finding all IPs that serve a specific SHA. So if I have a SHA in mind, which has a specific detection, like a known malware, then I can find all of the IPs that are serving it in our database. Finding another query is, of course, finding redirected domains, and for that matter, URL shortening services. So we found that experimentally, if, for example, a domain has a lot of URLs that are themselves redirecting to other URLs, then most likely that is an URL shortening service, or it can also be a compromised domain. Okay, another query is finding other domains sharing the same NS/MX servers, and this relates to passive DNS. Of course, you can also do the passive DNS queries, like finding all of the domains that are hosted on an IP and all of the IPs connected to a domain. So you can do both queries pretty easily in the graph. And one complicated query, and I'll let you digest this, finding IPs and domains which served SHAs which were dropped by dynamic analysis by SHAs coming from a specific IP. So this is kind of the power you get by using a graph database, at least for threat intelligence. And a final reason for using this model is, of course, flexibility. You can easily tack on new information as well as new entities as you're developing your threat intelligence system. Okay, one other thing I would like to talk about are the way we're scaling it up. So this is a work in progress right now. We've decided to use something like Data Center OS and Apache Mesos. This lets us deploy a lot of useful distributed services quickly and scale up our processing quickly. So every service in Mesos and Data Center OS gets its own container, and you can easily scale services by defining how many instances you'd like to run of that service. And each service, each major service, like Redis, Elasticsearch, RabbitMQ, ArangoDB, Storm, has its own, let's say, monitor for that specific service. So if an instance of that service goes down, the monitor will automatically start a new instance on a different Apache Mesos node. In order to run on Mesos and Data Center OS, you also need to containerize your different components. And right now we have containers for the phishing engine, the static analysis part, and different other things that we have in our system. And also for the actual graph with the related nodes in it, we're planning on using Apache Storm. So the Apache Storm framework lets you specify the topology directly, and you also get a lot of nice features like tracking through which nodes in the system a message went through while processing, as well as, for example, automatically retrying processing for a failed message and other interesting stuff like that. Now, while developing our system and scaling it up, we found a lot of interesting principles, let's say. One of them that was really useful was splitting up the components. So if you're developing such a system, try and split the components up while at the start. So This way, you don't end up with a big monolith that does everything, and that's really really hard to update and upgrade. Okay, another principle is when you're doing the component split, also split your data. This lets you scale the database for each component individually for your needs. Another principle is use a common and battle-hardened infrastructure components across your whole system. This means common logging, common caching, common message queue. So we're in our system right now, we're using RabbitMQ as a message broker, and let's just say that at the start of our system, when we were developing it, we had a lot of proof of concept components that were using it in slightly different ways, and you'd get crashes and other stuff by not having everything commonized. Okay, the final principle is also when you're scaling up and you have a lot of things to process, is to move the code to where you have your data. So this was really apparent in our passive DNS system, where a lot of records come in for storing in the DB, and it's much more efficient to do batch processing of them. So instead of doing 1,000 insert operations against the DB, you just do one operation and have all of the records to be inserted in that specific operation, and then apply the actual DB operations and have them run inside the DB server. Okay, so this was it from the engineering side. Now we're going to take a look at a few stats we've seen in our system. So one particular stat over here is the number of active Rapsheets still considered malicious by age. This is basically a histogram showing how old are our IPs in the database right now. So I said active because we also have a rescan process. So if something is considered malicious, it's kept in the DB and checked daily. If after 1 day no new malicious results come back, it's checked after 2 days, and then after 4, and then finally gets removed from the DB. So this basically is a histogram of the age of our active malicious IPs in the database. And you can see there are a lot of spikes over there, most of them corresponding to moments in time where there was a specific campaign. So as you can see, there are also a lot of IPs that are persistent over time. So we launched our system a year and a half ago, and as you can see, we have a few IPs that are more than 270 days old. So the URLs associated with those IPs rarely get cleaned up. Another stat over here is the delisted IPH distribution. So these are basically IPs which were active at one point in time, and then they became inactive. There's nothing malicious there anymore. As you can see, most of them tend to get delisted after around 30 days. And afterwards, you have a pretty long tail. So as you can see from the previous graph, we also have IPs that got delisted as after 250 days, for example. Okay, so most of them, and this makes it a really dynamic system, get delisted after 30 days. Okay, one final stat, and that is the malicious IP addresses by country. So you'll most likely recognize this. We have the usual suspect. This is based on the top 20 countries in our database. So the usual suspects are US, China, and Germany, and you'd expect that because these are the countries that also have the most IP ranges associated with them. So it's normal that attackers will use IPs from a lot of IPs from those. But we also get some surprising results in the form of Vietnam and Indonesia, which have few IP ranges but constitute quite a bit of, quite a lot of them are malicious. Okay, so that was it. If you guys have any questions or comments for us related to, okay.
Thank you very much. I have a question. When you say malicious IPs, what are they? Like sandbox things that are in sandbox,
So
or what?
malicious basically means we have proof that they're entertaining malicious activity. For example, they're serving URLs with malware on them, or they're part of a botnet, or they're serving phishing pages.
Or
Okay?
they're trying
Okay.
to actively exploit servers.
Yeah.
Right, like touching honeypots with malicious behavior.
Let me just get to the slide on that. So this is what we consider malicious. So if they're serving malware, then they're malicious. If a honeypot of ours received an exploit from them, then those IPs are malicious as well. If botnet samples tried from within our sandbox to communicate with them using the botnet CLC protocol, then they're considered malicious. And if they served phishing pages, then they're considered malicious as well. So we have 4 main categories right now. You can also add a 5th one, for example, if they redirect to a malicious URL. Yep.
Sorry, I have another question, which is, how do you handle malicious IPs that are compromised? Do you consider them infected or clean, or do you have a special status?
So if that particular IP is compromised, then we consider it infected. But you can also have the scenario in which you have multiple domains on a specific IP. In that particular case, we only consider the malicious domains to be blocked. So in the actual device that's using all of this data we're collecting, the decision is made first on the IP, and if the IP hosts multiple domain, a thing which we generally deduct by using passive DNS, then we only block the malicious domains. So we the device that then actually does the packet inspection and looks at the host name.
Any other questions?
So, okay, I've heard, so if we share the information, right? So, yes, we're trying to build collaborations, for example, with VirusTotal or Reversing Labs, and exchange malicious binaries with them, as well as URLs, IPs, domains. So basically, it's an exchange of information. The main difference here is that we actually do the work for proving that those URLs are malicious, not just take them from someone else and just put them in the database.
Any other questions?
If you have any more detailed questions, you can also find us at our stand, and you can also try the actual product that's using this information.
Did you consider any legal aspects
Legal aspects in what sense?
when you are publishing an IP and you declare it malicious?
Okay, so we didn't consider any legal aspects right now. It's up to the clients that use our threat armor device to decide whether the IP should be blocked or allowed. So in the actual device, even though we're marking it as malicious, the client can decide to allow access to it or ban it, or let it be banned, actually.